Okay, so we were talking about subharmonic functions and the solution of the Dirichlet problem using the Perron method. So I just wanted to make one remark before proceeding that we gave a definition of subharmonic functions for continuous functions, right? So the definition was that if U is continuous on a domain D, then U is subharmonic if for all say domains open sets V contained in D such that V closure is a compact subset of D. If H is a harmonic function on V, which is continuous on V closure, and H is so if U is less than or equal to H on boundary V, then U is less than or equal to H on V, right? So this is the definition we give. And we saw as a consequence, this implies that if B is any geodesic ball in D with B closure contained in D, and suppose B is a ball with center X, okay, then U satisfies the sub-mean value property. So let me call the center X naught actually. Okay. So U satisfies the sub-mean value property with respect to harmonic measure based at the center of the ball. So U of X naught is less than or equal to the integral over the boundary of the ball, U of xi d mu X naught d of xi, right? So we showed that 1 implies 2. Right? Because you just take, given the ball B, you let H be the solution of the Dirichlet problem in the ball B. With boundary values equal to U restricted to boundary B. Okay. Then U is less than or equal to H on boundary B, which implies by property 1, U is less than or equal to H on B, which implies U of X naught is less than or equal to H of X naught. And H of X naught is exactly this integral that we have here over boundary B of U of xi with respect to harmonic measure based at the center X naught. Okay. So 1 implies 2. Is this clear?
Yes.
And conversely, we can also show that actually 2 implies 1. So actually this submean value property with respect to harmonic measure this characterizes subharmonic functions. So how do we prove 2 implies 1? The point is, so in this case, we're given V an open subset of D such that V closure is a compact subset of D, and we're given H harmonic on V and continuous on V closure. And U less than or equal to H on boundary V. Okay. So then you look at the function, say, phi, which is U minus H. Okay. So this is a continuous function on V closure. Okay. And since H is harmonic, H satisfies the mean value property with respect to harmonic measure, right? And U satisfies the submean value property. So then that means that U minus H, which is phi, satisfies the submean value property.
Yes.
With respect to harmonic measure. But then we saw that if you have a continuous function which satisfies the submean value property with respect to harmonic measure, right, then it satisfies the strong maximum principle, right?
Yes.
Yeah, we did this proof last time. So we proved the strong maximum principle for subharmonic functions just using the submean value property, right? It's just like the proof for subharmonic functions in Euclidean space, right? Yeah. So that means phi satisfies the strong maximum principle. And that means phi satisfies the weak maximum principle. Right? The strong maximum principle implies the weak maximum principle. And so the weak maximum principle says that if we look at phi on boundary of this open set V, then there phi is less than or equal to 0 because U is less than or equal to H. So phi less than or equal to 0 on boundary V implies that phi is less than or equal to 0 on V. And that is what we wanted to prove, right? That means that U is less than or equal to H on V. Okay, is this clear?
Yes.
Yes, sir.
So we can take, just like in Rn, we can take the submean value property as the definition of subharmonicity for continuous functions. Just the only difference is that the submean value property is not with respect to Lebesgue measure on the sphere. It is with respect to harmonic measure on the sphere. Is this clear?
Yes, sir.
Okay. So this property too is sometimes easier to check, right? So this is also a useful characterization of subharmonic functions. The one thing which we don't have yet, which I'll think about, I don't have a proof of this yet, is that if U is a C2 function, then we saw that if Laplacian U is greater than or equal to 0, then U satisfies these two equivalent definitions, right, for continuous functions, right? So any C2 function with Laplacian U greater than or equal to 0 is subharmonic. In this sense, it satisfies the submean value property. That we proved, right? The only question which remains is the converse, that if U is C2 and satisfies the submean value property, then is Laplacian U greater than or equal to 0, right? So in other words, for C2 functions, we want to say that Laplacian U is subharmonic if and only if Laplacian U is greater than or equal to 0, right? So we've proved one direction, that if Laplacian U is greater than or equal to 0, then U is subharmonic. The converse, I don't have a proof yet. I'll have to think about it. That if U is subharmonic in C2, then Laplacian U is greater than or equal to 0. Okay. So, I mean, this we can prove, I can prove this for harmonic manifolds, because on harmonic manifolds, the harmonic measure is the same as the Lebesgue measure, right, on the sphere. And there we prove for a harmonic manifold, we prove that the Laplacian is given by the infinitesimal mean value, right? In other words, you look at mean value over a sphere minus the value at the center, divide by the radius squared, that converges to 1 over 2n times the Laplacian, right? So if you satisfy the submean value property, then the mean value minus the value at the center, this is greater than or equal to 0. You divide by r squared, you pass to the limit as r tends to 0, you get that the Laplacian is greater than or equal to 0. Is that clear? Yeah. So this is, we have this for harmonic manifolds. I just have to think, what about general Riemannian manifolds? It's still true, but I'm not, I haven't found a proof yet. So I'll think about that. Okay. So, if you can think of a proof, then that's good. You can let me know. I have to think about that. So, yeah, so let me just note that. So, and Okay, so 1 is equivalent to 2. And U in C2D, then Laplacian U greater than or equal to 0 implies 2. Okay. So the converse this is true, but we need a proof. All right. So think about it. Maybe you can come up with a proof. I have thought about it a bit. I still don't have a proof for the general manifold. For harmonic manifolds, yes, we have a proof. Okay.
So what we're saying about the infinite, we on general Riemann manifolds we have the infinitesimal mean-value property, right?
On harmonic manifolds, yeah. So see the
But
converse.
it is with
See, how do you prove the converse for harmonic manifolds? So suppose U is a C2 function where D is a domain in a harmonic manifold M, right? Then uh, for all x naught in D, we know what the infinitesimal mean value property says, that 1 over, okay, and so yeah. So let me suppose that U satisfies the submean value property too. Okay. So then for all x naught in D, 1 over 2n times the Laplacian of U at x naught. This we showed is given by the limit r tends to 0, 1 over r squared into the mean value. So that is the integral over, well, let me write it this way. The integral over the unit tangent sphere at x naught, U of x sub x naught of RV d lambda x naught of V divided by Cn. So this d lambda x naught is the Lebesgue measure of the unit sphere, and I'm dividing by Cn, which is the volume of the unit sphere. So this is the normalized Lebesgue measure. It's a probability measure, right? So this is the mean value over the sphere of radius r, right? So this minus U of x naught, this divided by r squared, this converges to 1 over 2n times the Laplacian of U at x naught, right? This is the infinitesimal mean value property for harmonic manifolds, right?
yes.
Okay. But now we know that for a harmonic manifold, harmonic functions satisfy the mean value property, right? So that means the value of a harmonic function at the center of a ball is equal to the integral with respect to this Lebesgue measure on the surface of the ball, right? Normalized Lebesgue measure on the surface of the ball. That means what? That means that the harmonic measure equals this normalized Lebesgue measure on the surface of the ball, right? So this integral
Yes.
is nothing but the integral with respect to harmonic measure, right? This integral is the same as the integral over the boundary of the ball of radius r, u xi d mu x naught b x naught r xi minus u x naught. And this, now this difference is greater than or equal to 0 because u satisfies the submean value property, right? Therefore, this limit is greater than or
Yes.
equal. So that's the proof, okay?
So for a general Riemannian manifold, we have the infinitesimal mean value property, but in terms of the, this surface volume of the sphere, that
No,
the
no, 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 no,
submean.
no, 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 no. We have to prove it. We've only proved the infinitesimal mean value property for harmonic manifolds. We have not proved an infinitesimal
Okay.
mean value property for general Riemannian manifolds. We do not have that. No,
Okay.
we did not prove that, right? We proved it for harmonic manifolds. Right.
Okay. Okay.
So probably what is true, but I don't know a proof of this, I have to see, is that if we take the mean value with respect to harmonic measure minus u of x naught, then this divided by r squared, this should hopefully converge to the same limit, which is 1 over 2n times the Laplacian. Okay. But I don't know a proof of that. Okay, so there should be an infinitesimal mean value property with respect to harmonic measure in a general manifold. All right. But I haven't seen any proof of this anywhere. Okay. So be careful. Utsav, is this clear? The mean value infinitesimal mean value property we proved was only for harmonic manifolds. Yes?
Yes, sir. Yes.
Oh, sorry. No, you're right. No, we proved, I'm sorry. What I, no.
If I remember that
No,
we
you're right.
actually
No, we
proved that
proved that
for general Riemannian manifolds,
yeah, but the problem is that the mean value that we're
two
taking.
measures don't
You're right.
coincide.
The
Yeah.
measures may not coincide. Yeah.
Right.
The mean value that we're taking here, this is coming from the unit tangent
Yes.
sphere, right? And this measure in general
Right.
is not equal to the harmonic measure. That's sorry, you're right. We proved
That-
the infinitesimal mean value property for general manifolds. You're absolutely right. Sorry, my mistake.
Yeah.
But
But the submean value property is in terms of the harmonic measure, which doesn't coincide with the surface volume measure. That is the problem.
Exactly. That is the problem. Yeah. So this coincides for harmonic manifolds. This coincides for harmonic manifolds. Yeah. So that's it. Exactly. Sorry. You're right. No, we proved the infinitesimal mean value property for general Riemannian manifolds. But we have to be a bit careful. Okay. Look, there are actually 3 measures in the picture. If you've realized. So see, there are actually 3 measures that we're looking at. Do you see what those 3 measures are? In a general Riemannian manifold, there are 3 measures on the sphere of radius r. Any idea what those 3 measures are?
Yeah, one is obtained like this from the unit tangent sphere. We look at the diffeomorphism exponential. One we get by that. The other one is the harmonic measure, and the third one is that we restrict the Riemannian measure on the sphere.
Well, we restrict the Riemannian metric on the sphere, and then we take the volume measure of the sphere.
Yeah,
the Riemannian volume
the
measure.
induced measure. Yeah.
Right. We take the Riemannian volume measure of the sphere. So yeah, so there are three measures. So one is this, you have the unit tangent sphere, and we have this diffeomorphism, say phi r, v maps to x naught rv, right? This goes from the unit tangent sphere to the sphere of radius r. Okay. So there are three probability measures. On the boundary of the ball of radius r that we can look at. So one is you take the, as you're saying, the Lebesgue measure, the normalized Lebesgue measure on the unit sphere, push it forward by this diffeomorphism. V goes to x naught rv. Okay, so phi r star of d lambda x naught over Cn. All right. This is one measure. The second measure is the surface area measure. So surface area measure is d vol of the boundary sphere. Okay, so this is the Riemannian volume measure of the boundary of the ball divided by the volume of the boundary to get a probability measure. Okay, and the third is harmonic measure, mu x naught p. Harmonic measure. Okay. So the nice thing is, for a harmonic manifold, all these three are equal. Okay. And for a general manifold, all three could be different. Do you see?
Yes.
So, see, all three are mutually absolutely continuous. So, if I call this first measure, let's say mu1, and this is mu2, and this is, say, mu3, then the mu i's are mutually absolutely continuous. Okay. So, so what is the, let's say, Radon-Nikodym derivative, d mu2 by d mu1. So at a point x naught of rv, what is the first Radon-Nikodym derivative going to be? It's going to be up to a constant. It's going to be the Jacobian, JVR. Right?
Yes.
Okay. And what about the, so that gives the relation between the first two measures. And what about the relation between mu3 and mu2? Well, we know that harmonic measure, d mu3 with respect to d mu2 at a point, say, xi on the boundary of the ball. So, okay, this is a point V here. At a point xi, this is going to be minus, up to a constant, minus the normal derivative of the Green's function for the ball with respect to, with pole at x0, right? No, minus the normal derivative, right? This at the point xi. Okay. Is this clear?
Yes.
Okay, so so in general, all these measures will be different. It's only we've shown for a harmonic manifold, all three are the same, right? So there, the mean value property you can take with respect to any of these three measures. They're all the same measure. But on a general Riemannian manifold, if you take the mean value, then, well, you'll get different answers with respect to these three measures in general, right? So is that clear? Yeah, any questions? Okay, so I mean, for subharmonic functions in a general Riemannian manifold, you should take the submean value property with respect to the third measure, which is harmonic measure. Okay, that is the one which will give you subharmonic functions. All right. And for a general Riemannian manifold, if you take the infinitesimal mean value with respect to the first measure, then you will get the Laplacian. Okay, so is this okay?
Yes.
Rudrada, any question?
No, no question. So you said with respect to the first measure, you will get the Laplacian. That means what actually?
That means this formula here, this infinitesimal
Okay,
mean value
yeah,
property.
okay. Okay.
This is in a general Riemannian manifold. So this is the
Mhm.
integral of u with respect to the first measure, which is coming from the unit tangent sphere.
Okay,
And
yeah.
in a harmonic manifold, this is the same as the
Same as.
harmonic measure. And so therefore, if you satisfy the submean value property, this is going to be greater than or equal to 0. So that's it. But in a general Riemannian manifold, these two measures will be different, right? So
Right.
So we can't immediately conclude that the Laplacian will be greater than or equal to 0. I'll have to think about that. It's true, but I have to think about it. Yeah. Think about it. Yeah. Okay, let's stop this session and start a new one. There's less than 1 minute. So. Okay. All right. So now let's come back to the Perron method. So we're given a precompact domain D, a Riemannian manifold, and we have a continuous function phi on the boundary of D. So then we define the Perron family associated to phi to be the following family of subharmonic functions, f sub phi. These are continuous functions on the closure of D, which are subharmonic on D and which are less than or equal to phi on the boundary of D. Okay. So notice that if I take the constant function infimum of phi over boundary D, then this clearly belongs to this Perron family. So this Perron family is non-empty. And also, since subharmonic functions satisfy the strong and weak maximum principle, since u is less than or equal to phi on the boundary of D, that means that u will be less than or equal to the sup of phi on the whole of D, right? Okay. And so that means that all the functions in the Perron family are uniformly bounded above by a constant, this sup of phi. Okay. So therefore, we can define the Perron solution. We can define this function, which is called the Perron solution. This is a function in the domain D. U phi of x is the sup over u in the Perron family of u of x. Okay, so take the supremum pointwise over the whole Perron family. So this supremum is finite, since all of these are bounded above by the sup of phi. And since the function inf of phi belongs to the Perron family, this supremum is greater than or equal to inf phi and also less than or equal to sup phi. Okay. So this Perron solution is bounded above and below. Okay. And we observed earlier that if the Perron solution is continuous, then it's easy to see that it is harmonic, right? Because let me just recall the proof of that for you. So if the Perron solution u phi is continuous in D, then it is harmonic in D. So to see this, what you do is you have your domain D. You take any geodesic ball E in D. So B is a geodesic ball such that B closure is contained in D. Then you take the harmonic lifting, right? Of so you let V be the harmonic lifting of the Perron solution with respect to the ball B. So we can take this harmonic lifting because we're assuming that U phi is continuous, right? So to define the harmonic lifting, what do? We take the continuous function, restrict it to the boundary of the ball B, and then take the harmonic extension into the ball B, right? And you define the harmonic lifting to be equal to the function outside, right? So then we know that if U phi is continuous, then because it's a supremum of subharmonic functions, it will also be subharmonic, right? That's easy to show. Just the same way that you show that a maximum of subharmonic functions is subharmonic. Similarly, you can show if you take a supremum of subharmonic functions and the supremum is continuous, then it is subharmonic. So this V will be also subharmonic, this harmonic lifting. And V will be greater than or equal to, and on the boundary of, on the boundary of the domain D, V is also less than or equal to phi. Okay, well, yeah. No, actually, okay. Actually, there's a slight problem with this argument. So what I want to say is that V also belongs to the Perron family. So for that, I need that V is less than or equal to phi on the boundary. That is not clear. That is not clear. Oh, okay. Yeah. That is not clear. No, actually, okay. So, okay, if we know that, all right, so let me make another assumption. So if I assume that U phi is less than or equal to phi on boundary D, then we can show that it is harmonic on D, because outside the ball B, V is equal to U phi, and this is less than or equal to phi on boundary D. So then V also belongs to the Perron family, and that implies that V is less than or equal to U phi. By definition, U phi is a supremum over all elements of the Perron family. So V will be less than or equal to U phi, and U phi will be less than or equal to its harmonic lifting, right? Which is V. So that means that U phi is equal to V, which is harmonic in B. So therefore, U phi is harmonic in B. Okay? And since B was an arbitrary ball in the domain, that means that U phi is harmonic in the domain. Okay. All right. So this is not very satisfactory. We had to assume two properties, right? One is that U phi was continuous in the domain, and two was that U phi is less than or equal to phi on the boundary of the domain. Right? We had to assume actually it's continuous on D closure, and U phi is less than or equal to phi on boundary D.
Sir,
So, I mean, these two properties are not obvious, right? So I'm just saying that if we had these two properties, then it's easy to see that it's harmonic. So, Okay, so I'm not saying that, these two properties hold. I'm not saying that. I'm just saying that if they hold, then it's not hard to show that the Perron solution is harmonic. Okay. Yeah, question?
So U phi is not always less or equal to phi on the boundary.
No, that's not clear, right? Because we're taking a supremum. So why should it be equal to phi on the boundary? Why should it even extend continuously to the boundary, right? Because I'm taking
Phi.
subharmonic functions which are less than or equal to phi on the boundary. My subharmonic functions are not equal to phi on the boundary. That is not the assumption, right? They're less than or equal to phi on the boundary. So right, I mean, if I take a boundary point, say xi, I'm taking a point x which is close to xi. I'm taking the supremum of all subharmonic functions here, right, in the Perron family at the point x. So those subharmonic functions, I mean, all of them are less than or equal to phi at the point xi, but their values at x could be larger than the value of phi at xi, right? So it's not clear that the Perron solution is going to be less than or equal to phi on boundary D. So neither of these two hypotheses is clear, and they may not be true in general. I'm just saying this is a heuristic motivation to see why the Perron solution might be harmonic, right? This is just some heuristics. Okay. This is not the proof that the Perron solution is harmonic. So that proof we're going to do now. Okay. So that proof is slightly different. So we have the following theorem that the Perron solution, in fact, is always harmonic in the domain D. Okay. So we're going to show that if we take any point x naught and we take a geodesic ball around x naught whose closure is contained in D, then we'll show that the Perron solution is harmonic in this ball. Okay. So first of all, by the definition of the Perron solution as a supremum, at the point x naught, it's the supremum of functions in the Perron family, right? Their values at x naught. So that means there exists a sequence un in the Perron family such that un of x naught converges to u phi of x naught, right? And now these functions un, these are in the Perron family. We can always, so these are bounded above by the supremum of phi, right? But we can also assume that they're bounded below, because we just take the maximum of un and the infimum of phi, this constant, right? So this is the maximum of two subharmonic functions. So this is subharmonic, and on the this is subharmonic and continuous, right? Because it's a maximum of two continuous functions, so it's continuous. And this is also less than or equal to phi on the boundary, right? So therefore, this function also lies in the Perron family. Yeah. And this is also going to converge to u phi of x naught, right? Because u phi of x naught is greater than or equal to the infimum of phi, right? We know that on the whole domain, u phi is greater than or equal to the infimum of phi. Yeah. So if we replace un by this sequence, max of un and inf phi, then this will also converge at x naught to the value of u phi at x naught, right? And so therefore we can assume, once we take this sequence, then replacing un by this sequence if necessary, we can assume that un is greater than or equal to in phi and less than or equal to sub phi for all n. Is this clear?
Yes.
Yeah, okay. Okay. So now we have a uniformly bounded sequence of subharmonic functions which are converging to the supremum over the Perron family at x naught. Okay. So now what do? We take Vn to be the harmonic lifting of un. Right. So this we know this will belong to the Perron family, right? Okay. So we take the harmonic lifting in this ball B. Then what do we know? We know that the harmonic liftings Vn are greater than or equal to the uns, which are greater than or equal to in phi. And the harmonic liftings, because they belong to the Perron family, they're less than or equal to sub phi. Okay, so the Vn's are also bounded in between in phi and sub phi. And so they're uniformly bounded. And Vn of x naught is greater than or equal to un of x naught. And it's also less than or equal to u phi of x naught, because u phi is the supremum over all elements of the Perron family. And the Vn's belong to the Perron family. Right? So Vn x naught is sandwiched in between these two. And so since un x naught converges to u phi x naught, we get that Vn x naught also converges to u phi x naught. Okay. So now we are getting a sequence of subharmonic functions in the Perron family, which converge to the supremum at x naught, but they are also harmonic on the ball B, right? In a neighborhood of x naught. So what we want to say is that on the ball B, because these functions Vn are uniformly bounded, convergent subsequence which converges to a harmonic function in the ball B. Okay, so there are two ways to see this. One is using, as I've written here, using the Harnack-Yau inequality. Alternatively, we can use the interior Schroeder estimates. So let me recall for you the interior Schroeder estimates, which we proved here. So yeah, we have this proposition. Right. So if you had L, which was a elliptic second order operator with locally ordered coefficients in a domain D and Rn, and if UNs are C2 alpha functions on D, which are L harmonic, then if this sequence is uniformly bounded on compacts in D, then there is a subsequence UNK and an L harmonic function U such that UNK converges to U uniformly on compacts in D. Right? So we prove this proposition using the interior Schroeder estimates. So here our functions are the Vn's, which are uniformly bounded on the ball B. Right? So there's going to be a subsequence which converges uniformly on compacts in the ball B to a harmonic function in B. Right? Is this clear?
Yes, sir.
Okay. So that's why we wanted our these Vn's to be uniformly bounded above and below. Okay. So then these are going to converge. So Vn's will have a subsequence which converge uniformly on compacts in V. So say some subsequence Vnk converges to V, and V is harmonic in B. Okay. So therefore, we have this harmonic function V on B, so that Vx naught, this is equal to the limit of Vnk x naught, which is U phi x naught, right? So Vx naught is equal to U phi x naught, and this harmonic function V is less than or equal to U phi on the ball B, because all the Vn's, these were elements of the Perron family. So these are everywhere less than or equal to U phi, right? the Perron solution. So their limit will be less than or equal to U phi. Is this okay?
Yes, sir.
Yeah. Now the claim is that the Perron solution U phi is equal to this harmonic function V in the ball B. Okay. So that will prove that U phi is harmonic in the ball B. And we're done. Okay. So suppose not. So then at some point X in the ball B, we have that Vx is strictly less than U phi of X, right? Okay, we already know that V is less than or equal to U phi. So if V is not equal to U phi, then we get a point where this harmonic function Vx is strictly less than U phi X, right? So now U phi is the supremum over the Perron family. So if Vx is strictly less than the supremum, that means there exists a U in the Perron family such that Vx is strictly less than Ux, right? Okay. So now take this sequence of harmonic functions V and K, which were converging to V uniformly on compacts in B, and let UK tilde be the maximum of U and V and K. Okay. So now let capital UK tilde be the harmonic lifting of little UK tilde in the ball B. Okay, this UK tilde is a maximum of two elements of the Perron family, right? This U and V and K. So this is also in the Perron family. It's subharmonic. So we can take its harmonic lifting, right? Okay. And so this UK tildes will also be uniformly bounded, right? Because this UK tilde lies in the Perron family. So it is less than or equal to the supremum of phi, right? Everywhere in the domain D. And the V and Ks are greater than or equal to the infimum of phi, right? Everywhere in the domain D. Right? So therefore, the maximum of U and V and K will also be greater than or equal to the infimum of phi. Right? So that means these UK tildes, capital UK tildes, these will be bounded above and below. Right? So they're uniformly bounded. So therefore, they have a subsequence again, which converges uniformly on compacts in the ball B to a harmonic function U tilde in B. Right? Okay. Now, these capital UK tildes, these were greater than or equal to the little UK tildes, which are greater than or equal to the V and Ks, right? So when I pass to limits, that will tell me that this limiting harmonic function U tilde, this is greater than or equal to V, right? Okay. And on the other hand, V at the point x naught is already equal to U phi at x naught. And U tilde at x naught, this is also going to equal U phi at x naught, because U tilde at x naught, this is the limit of UK tildes of x naught, and capital UK tilde is greater than or equal to little UK tilde, which is greater than or equal to V and K, right? And V and K x naughts are converging to U phi x naught. So that will tell you that U tilde of x naught is equal to U phi x naught. Is this clear?
Yes, sir.
Okay. So what does that mean? That means if I look at the harmonic function V minus U tilde, right, in the ball B, then this is less than or equal to 0 in the ball B, but it takes the value 0 at the point x naught. Therefore, by the strong maximum principle, it is identically 0. In other words, V is equal to U tilde, right?
Yes.
Okay. But now, by the way we've constructed U tilde, what do we have? U tilde is the limit of these capital UK tildes, which were the harmonic liftings. These harmonic liftings are greater than or equal to little UK tilde, and little UK tilde is greater than or equal to little u, right? So that means that U tilde, capital U tilde, will be greater than or equal to UX, but this UX we chose to be strictly greater than VX, right? So then we get U tilde X strictly greater than VX. That's a contradiction, right? Since V is equal to U tilde. So is this okay?
Yes.
Okay, so therefore, the Perron solution U phi is equal to the harmonic function V in B. And so that means U phi is harmonic in B. And therefore, it's harmonic on the whole domain D, since this ball B was an arbitrary ball in the domain D. Okay. Is this all right?
Yes.
So okay. Any questions about this proof? It's a bit long proof, so that's why I'm just asking if it's okay. Okay. All right. So we've got that the Perron solution is harmonic in the domain D, right? So what remains to show now is that this Perron solution has the right boundary value, right? So we want to show whether or not U phi of X converges to phi of Xi as X converges to a point Xi in the boundary of D, right? Okay. Yeah, this is what remains to show. Then we will have our solution to the Dirichlet problem, right? We
Yes.
just need to show that Perron solution has the right boundary values. Okay. So for this, classically, the concept that is needed is what is called barriers. Okay. So, so let me give you the definition. So let Xi be a point in the boundary of D. Okay. So then a function W, which is continuous on D closure, is called a barrier at Xi if, first of all, W is superharmonic in D. And secondly, W at the point Xi is 0 and W is strictly positive at all X outside the closure of outside the point Xi in the closure of the domain D. Okay, for all X in D closure minus Xi. So let me give you an example of a barrier. This is the example we'll be using later. So suppose your domain D is like this. Suppose it's a ball with center at the point, say, minus E1, okay, in Rn. And so this is the hyperplane x1 equal to 0, right? Yeah. So if I take, for example, the function, say, minus x1, right? Then this function is in fact harmonic, right? For the Euclidean Laplacian, and it is 0 at the point, this point xi on the boundary, which is the origin. Okay, and it is strictly positive at all other points in the domain, right? Yes.
Yes.
So Laplacian W is 0. So 0 means it's harmonic. In particular, it's superharmonic, and W of xi is 0, and W is strictly positive on D closure minus singleton xi, right? Yeah, so it's a superharmonic function which attains its minimum at the boundary point xi, right? We know by the maximum principle, a superharmonic function can only attain its minimum at a boundary point, right? So here the superharmonic function is attaining a strict minimum at this boundary point xi. Okay. All right. Yeah, so this is an example of a barrier. This is the main example we'll need, really. So how can we use a barrier? Right. So first of all, a barrier is a function which is defined on the whole domain D closure. But we don't need a function defined on the whole of the domain. In fact, a barrier is a local concept. We can define what's called a local barrier at xi. That means there is a neighborhood n of xi such that W is a function which is continuous only in this domain D intersect the neighborhood. Okay, the closure of that. So in a closed neighborhood of xi, intersect the domain. And in this neighborhood, W satisfies these two properties. It's subharmonic in D intersect this neighborhood N, and it has a unique minimum at the point xi, right? So Wxi is 0 and Wx is positive for all x in D intersect N closure minus xi. All right. So, I mean, we'll get a local barrier if your domain looks like this sphere near the point, near the origin. So maybe the domain over here looks like this, like a sphere, and then afterwards it looks like something else. Okay. Right. Okay. So, I mean, what do I mean? So maybe a better picture would be maybe the domain looks like this. So then I can't take this minus x1 as my barrier globally, right? Because globally it's not going to have a minimum at xi, right? The minimum will be somewhere here, right? Okay, so I can't use this as a global barrier, but I still have it. This still works as a local barrier, right? If I take my neighborhood N of xi, then in this neighborhood, this point xi is still the unique minimum of my superharmonic function here, right? Okay. Is this all right? Yeah.
Yes, sir.
Okay, so this will be my domain D intersect N. Yeah. So I take the closure of that. So I want a locally defined function. Okay, in this neighborhood intersect the domain. Okay, which has a unique minimum, a superharmonic function, which has a unique minimum at xi. Okay. So the point is, if we have a local barrier, then we can always construct a global barrier. Okay, so well, I've done this here. So given a local barrier, the lemma says if there is a local barrier W at xi, then there is a barrier W tilde at xi. In other words, W tilde is globally defined. Okay, so how do we get this global barrier? So what we do is we take a ball B around xi, whose closure is contained in this neighborhood N. Okay, so in this picture, I'll take a smaller ball B here. Okay, like this. Okay, so this is the ball B. Okay, so given W, this is a local barrier. I want to, so this is superharmonic in this neighborhood of xi in D. I want to extend it to a global superharmonic function. So what do I do? Well, you take this ball B around xi whose closure is contained in N, in your neighborhood N. Okay. Then what we can do is, we know that outside this ball B, my local barrier W is strictly positive, right, by hypothesis. So what we can do is, you let M be the infimum over D intersect N closure, okay, this compact domain minus the ball B, okay, of W. So this is positive by hypothesis, right? Yes?
Yes, sir.
Now all I do is, I define my function W tilde to be equal to this infimum outside the ball B and inside the ball B. That means in D closure intersect B, I define it to be, so I want a superharmonic function. So the minimum of two superharmonic functions is superharmonic. So I define it to be the minimum of this. Oh. Okay, so we're showing that if we have a local barrier at a point xi, then we have a global barrier at xi, right? So the point is, we're given a superharmonic function in this domain intersect to neighborhood of xi, D intersect N closure, and we want to extend it, or we want somehow to construct a superharmonic function in the whole domain. All right.
So you have to share the screen.
Oh, sorry, I forgot. Sorry. Okay, yeah. Okay, so we have this picture, right? We have our local barrier W, which is defined in the domain D intersect a neighborhood N of Xi, the closure of that. It's continuous and superharmonic. So what do? We take a ball B whose closure is contained in N. So this ball B, a small ball around Xi. So we know that outside the ball B, by hypothesis, my local barrier is positive, right? So I take its infimum outside the ball B, okay? So M is the infimum over D intersect N closure minus the ball B. So this is a compact set. So this infimum is positive, right? Because W is positive outside the ball B. Okay. Then what do? We let W tilde, we let it equal this infimum outside the ball B. Okay, so outside I just let it be constant equal to this infimum. So, and inside the ball B, I just let it be the minimum of this infimum and Wx. Okay. So first note that this function is continuous, right? Because if I take a point, so these, I mean, the only place where I have to check continuity is when I am in D closure intersect the boundary of B, right? Okay. Yes?
Yes, right.
I have to check whether these two definitions agree. So if X belongs to D closure intersect boundary B, right? Then Wx is going to be greater than or equal to M, right? Since X belongs to then the complement of B, right? And M is the minimum, the infimum over the complement of B inside D intersect N, right? Okay, so that means that this minimum of MWX is equal to M. So these two definitions agree, right?
Yes.
Okay, so this W tilde is continuous. And then we have to check that it's superharmonic, right? So for superharmonic, we can either use the definition in terms of comparing with harmonic functions, or we can use the definition in terms of the submean value property, right? Okay. And the submean value property, you only need to check actually for small enough balls, right? If you look at the proof of equivalence of these two definitions of subharmonicity, all you need is that this submean value property holds for all R small enough, right? Because that's enough to prove that 2 implies 1, right? Yeah, there we needed that a function satisfying the submean value property. It satisfies the strong maximum principle, right? So for that, you only need small enough balls, right? You don't need it for all balls. You just need small enough balls. Is that clear? Yeah. Okay.
Yes.
Yeah, so here it's not hard to see that this function is so here's my domain xi. Here's my ball B. And my neighborhood N is, let's say, a larger ball, N. Okay. So, so I have to check that this function W tilde is superharmonic. Right. So, so because I just need to check the sub mean value property for small enough balls, this means that subharmonicity is a local property, right? Because I just need to check for small enough balls, right? So this is a local property. Okay. So in this case, we have that my W tilde is equal to M outside this ball B. So outside the ball B, W tilde is constant, right? So W tilde equal to M on D closure minus, let's say, the closed ball. So then this is an open set. So in this open set, W tilde is constant. So therefore it's superharmonic, right? Okay. So W tilde is superharmonic. On D minus B closure, right? Because it's constant there. And if I'm inside the ball, right, if I'm in D intersect B, then it's equal to the minimum of two superharmonic functions. Right. So W tilde is superharmonic in D intersect B, right? Is this clear?
Yes, sir.
So what is the problem? We just need to check points in the boundary of B, right?
Right.
Okay, so there we need to check the submean value property, right?
Yes.
Okay, so not the submean value, the supermean value property. We want to show that it's superharmonic, right? So let X be a point like this. Which is in D intersect boundary B. Okay, and let say, so I need to use some other ball, some other notation for a ball. So let me call it, say, B tilde is a small ball around X. So let B tilde be XR for R small. Okay. Right. So I have to show the supermean value property, right? So what do I have? I have I want to show the mean value over the boundary of B tilde of W tilde, right? D mu x B tilde, right? This I want to show is less than or equal to W tilde of x, right? But W tilde outside the ball B, this is equal to M, and inside it's the minimum of M and W. So it is always less than or equal to M, right? On this ball B tilde, right? So this integral is less than or equal to M, right? And we saw that for a point on the boundary of this ball B, W tilde is equal to M, right? Right. So this is the super mean value property. Is this clear? Yeah.
Yes, yes, right.
Utsav, is this okay?
Yes, sir.
Yeah. So we've proved the super mean value property at all points in the domain D then, right?
Right.
So that implies that W tilde is super harmonic in D. Okay. Okay. And now note, so note in D closure intersect B, W tilde of x, this is the minimum of M and WX, right? Okay. So this is well, either it's M or it's WX. So M is positive. If it's WX, then if X is not equal to Xi, then WX is positive, right? So this is going to be positive if X not equal to Xi, right? And if X is equal to Xi, then it's 0 because W of Xi is 0, right? So this is 0 if X equal to Xi. Right? So that means it satisfies the property of a boundary, right? Of a barrier, sorry. Right? It is positive everywhere except at the point Xi. Is this okay?
Yes.
Okay, so we've constructed a global barrier. Okay. So if you have a local barrier, then you can construct a global barrier. Okay, so I've given a different proof here that it's super harmonic. So you can have a look at that, but fine. Okay. All right, so now we have the following theorem that if phi is a continuous function on the boundary of D and Xi is a point in boundary D, then if there is a local barrier at Xi, then the Perron solution U phi of x, this converges to phi of Xi as x tends to Xi. Okay, so existence of a barrier implies that the Perron solution, it converges to the right limit at that point. Okay. All right, so what we need is really existence of a barrier at each point. Okay, that's what we need here. All right. So so let's see how to use the barrier. Okay. So let epsilon be given and put M to be the supremum of mod phi over boundary D. Okay. So now by the previous lemma, if we have a local barrier, then we may as well assume that we have a global barrier, W, right, which is continuous on all of D closure and which is a barrier at xi. Okay. So W is a superharmonic function whose unique minimum on D closure is attained at xi and is equal to 0 at xi. Okay. So now we can choose a ball B around xi such that by continuity of phi eta minus phi xi mod of this is less than epsilon for all eta in boundary D intersect this ball B. Okay. So now we know that our barrier W is strictly positive outside this ball B, right? So in D closure minus B, which is a compact, right? There my barrier W is going to be bounded below by a positive constant. Therefore, if I choose a large integer k, then I can ensure that k times W is greater than or equal to 2m, okay, where m was this sup of mod phi. I can ensure that k times W is greater than or equal to 2m for all x in D closure minus B, right? Okay. Yeah, because I know that outside the ball B, it's bounded below by a positive constant, right? It has a unique minimum as 0 at the point xi, right? So outside the ball around xi, it's bounded below by a positive constant. So if I multiply by a large integer, it'll be bigger than this 2m, okay? So now, using the barrier, the idea is to construct subharmonic and superharmonic functions, which will bound from above and below the Perron solution. That's the idea. Okay. So, for example, if we let U naught to be phi xi, a constant, minus epsilon minus kw. Okay. So then, first of all, this phi xi minus epsilon, this is a constant, and W is superharmonic. So minus kw will be subharmonic, right? So this is a continuous subharmonic function. And the claim is that this belongs to the Perron family. So we have to check that it is less than or equal to phi everywhere on the boundary, right? So there are two cases. So if I take, let's say, an eta, which is inside the ball B around xi, right? So there, phi eta is greater than phi xi minus epsilon, right? And this function U naught at eta, since W is greater than or equal to 0, this is less than or equal to phi xi minus epsilon, which will be less than or equal to phi eta, right? So that shows that for all eta inside boundary D intersect the ball B, this U naught of eta is less than or equal to phi of eta, right? And if I'm outside the ball B, then what happens is this k times this barrier W, this is large, right? This is bigger than 2m. So this will make this very negative. So what will happen is this phi xi minus epsilon minus kw, this will be less than or equal to phi xi minus epsilon minus 2m, right? And phi xi is less than or equal to m. So the whole thing will be less than or equal to minus m minus epsilon. So that is less than or equal to phi eta, right? For any eta in boundary D, right? Because m was the sup of mod phi over boundary D. So is this clear that this function will be less than or equal to phi everywhere on boundary D?
Yes.
Yeah, okay.
Yes.
So therefore, it belongs to the Perron family, F phi. Similarly, if I look at the function phi xi plus epsilon plus kw, this will be superharmonic and greater than or equal to phi on boundary D, right? Okay. All right. Yeah, so
Yes.
so what do we have? We have now using this barrier at xi, we have two functions. U naught is this constant phi xi minus epsilon minus kw. Okay, so this belongs to the Perron family. This is subharmonic, and I mean U naught is less than or equal to phi on boundary D. Okay, and similarly we have V naught, which is phi xi plus epsilon plus kw. Okay, this V naught is superharmonic, and this is greater than or equal to phi on boundary D. Okay, so now if I take the Perron solution, so by definition U phi of x, this is going to be greater than or equal to U naught of x, right? Because U phi is the supremum over all elements in the Perron family. And U naught of x, this is what? This is phi xi minus epsilon minus kw of x. So as x tends to xi, my barrier vanishes at xi, so this tends to 0, right? So this converges to phi xi minus epsilon as x tends to xi, right? Since w xi is equal to 0. Okay. And so what does that mean? That means I get one inequality, that the limit of the Perron solution U phi x as x tends to xi, this lim-inf is greater than or equal to phi xi minus epsilon, right? For all epsilon positive. And so then I can let epsilon tend to 0. And so what I get is that this lim-inf is actually greater than or equal to phi xi. Is this clear? Yes?
Yes, yes.
Okay. And now, if I take any U in the Perron family, okay, then if I look at the function V naught, well, okay, if I look at the function U minus V naught, okay, so then this is subharmonic on D, because U is subharmonic and V naught is superharmonic. So minus V naught is subharmonic, and the sum of subharmonic functions is subharmonic. So be careful to prove the sum of subharmonic functions is subharmonic. That is not so clear from definition 1. Okay, if you look at definition 1 of subharmonic, from here it's not obvious that the sum of subharmonic functions is subharmonic. But if you look at the submean value property, this definition, for this definition, it's clear that the sum of subharmonic functions is going to be subharmonic, right? Yes?
Yes, sir.
Right.
So from the second definition, it's easy to see the sum of subharmonic functions is subharmonic. So, so therefore, if I have this superharmonic function V naught, then U minus V naught is subharmonic on D. And U minus V naught is less than or equal to 0 on boundary D, because U is less than or equal to phi and V naught is greater than or equal to phi, right? On boundary D. So therefore, by the maximum principle, U is less than or equal to V naught on D for all U in the Perron family, right? But then by taking supremum over all U, this implies that the Perron solution U phi is less than or equal to V naught on D, right? Okay. So this implies that now I take limits, and so lim sup of U phi x, right? This will be less than or equal to limit V naught x, x tends to xi, and this is equal to phi xi plus epsilon, right? For all epsilon positive. And that implies that the lim sup is less than or equal to phi xi. Is this clear?
Yes, sir.
Okay. So that proves it, right? The lim inf is greater than or equal to phi xi, and the lim sup is less than or equal to phi xi. And so therefore the limit is equal to phi xi. Okay. Okay, so that's what we wanted to prove. Is this all right?
Yes.
Okay. Okay, so the last thing to complete the solution of the Dirichlet problem is to say that if the boundary of the domain is sufficiently smooth, then at each point we have a local barrier, right? That will tell you that the Perron solution converges to phi as you converge to the boundary, right? Okay. So the last part is now to construct barriers, all right? Is this okay? Yeah.
Yes.
So that's what this proposition says. So let D be a precompact domain with C2 boundary. Okay, so if you have C2 boundary, then for any xi in boundary D, there is a local barrier at xi. Okay, so I've written a proof, but let me just draw you the picture. It will be very simple what we're doing. Okay, so why do we need C2 boundary? Well, for the following reason. So D precompact with boundary D C2. Okay. So then for all xi in boundary D, there exists a local barrier at xi. So the proof is very simple. So you have your domain D. And because the boundary is C2, okay, what we can do is, given a point xi, we can take a neighborhood U of it, right? And this is my domain D. And I can take a coordinate chart, a phi, right? So first of all, I can take a coordinate chart which, let's say, maps boundary D to part of let's say, the left half space. Okay. So phi I can take to be, say, C2, because the boundary is C2, right? So boundary C2 means exactly that you have a C2 diffeomorphism which straightens out the boundary, right? That is the definition of C2 boundary. Okay, that I can map it a hyperplane with a C2 diffeomorphism. All right. Yeah, so this part now, this is, say, this hyperplane is, say, x1 equal to 0. All right. And so this part here, this is phi of U intersect D. This is contained inside x1 less than 0. Okay. Fine. Now, this hyperplane I can map by a further smooth diffeomorphism. I can map this to a sphere, right? Like this. Let's say a sphere with radius 1. Okay. This is the point, say, minus E1. And this is a sphere with radius 1. Right? Okay. So this is my x1 equal to 0. And so my xi maps to the origin here. This maps again to the origin here. Okay. So basically, my diffeomorphism phi maps me into the left half space here. And then I can further map this into a ball, right? Okay, so this will be psi composed phi of U intersect D. Okay, this is, let's say, contained inside the ball around the point minus E1 of radius 1. Okay. Yeah. And so the boundary is mapping to part of this sphere. Okay. Now, what happens? So I let, say, F be the composition, psi composed phi. So that's a C2 diffeomorphism from here to here. C2. Okay. And now my Laplacian over here becomes an elliptic second order operator over here on the right hand side, right? So I have an operator. So if I call this this domain here, so if I call V equal to f of U, right? Then I have an operator L on V, right? L of a function U is equal to Laplacian of U composed with F, right? So if U is a function here, right, then U composed with F is going to be a function on my manifold in this open set U, and then I take its Laplacian here, right? So this is a second order elliptic operator. Right? because my f is C2, this this U composed f will be C2, right? If U is C infinity. And so the Laplacian of it makes sense. It's well defined, right? Okay, this is second order elliptic without constant coefficient, with constant term 0. Right. So now I can take the same barrier that I had earlier. Right. In this picture, I just take my barrier W in this picture to be minus x1. Right. Okay. Then L of W will be 0, right? Because it's second order. So, I mean, oh no, okay. So, all right, okay. No, not minus x1. There are first order terms. So what I do is I take W to be, sorry, I take it to be so if I take e to the lambda x1, right, then by the same computation that we did earlier for lambda large, this is going to be subharmonic, right? And at this boundary point, this is this takes the value 1 when x1 is 0. So if I want a superharmonic function, I take 1 minus this, right? Okay. So this will be my
Yes.
superharmonic function. L of W will be less than or equal to 0. And so then I take my function, my barrier here will be, so let me call this W tilde. And my barrier W will, my local barrier W will be W tilde composed with F. Okay, so then Laplacian of this will be less than or equal to 0. It will be superharmonic and it attains a unique maximum at xi. Okay. Is this all right? Yeah.
Yes.
Okay, so
Yes.
so that gives the existence of a barrier for domains with C2 boundary, and hence the solution of the Dirichlet problem. Okay, so there's less than a minute. If you want me to continue, I can. Otherwise, we'll meet next week. Okay. So. Okay, so all right. So see you next week.